Yeah, we finally now get to talk about wrapper methods for feature selection. Previously, we talked about filter methods, which use intrinsic properties of features for the selection, for example, variance thresholds. And then we also talked about embedded methods where the feature selection is part of the algorithm, for example, the feature selection in decision trees. Now, in the wrapper methods, we use models explicitly for doing these feature selections. So one example would be recursive feature elimination, which is the topic of this video. And then in the upcoming videos, we will see also other methods for feature selection using wrapper methods. So yeah, just as an overview again, here are our three methods for feature selection, where today, the focus is on wrapper methods. Yeah, and conceptually, recursive feature elimination is actually pretty straightforward. So we can summarize the main approach in 3 steps. So the first step would be fitting a model to the data set. And usually for that, we consider a linear model or a generalized linear model, like linear or logistic regression, where linear regression would be a normal linear model, and logistic regression would be a generalized linear model. So considering that we have a linear model, the first step would be just fitting the model to the data set. So nothing really special here. And then we look at the model, and in particular, we look at the model coefficients. I will tell you in the next slides concretely how that looks like. So considering the model coefficients, we then eliminate the feature with the smallest coefficient. And we consider this feature with the smallest coefficient as the most unimportant one. One important aspect when we do this is that we have normalized, or let's say standardized our features, and we will see later in the code examples concretely how we can do that. I mean, it's nothing new, it's something you have been doing a lot of times. We will, in the code example, see concretely how the workflow looks like. So now let's get back to these 3 steps. Step 1 is fitting the model. Step 2 is eliminating the feature with the smallest coefficient. And then the last step is essentially just repeating steps 1 and 2 until we reach the desired number of features. So it's essentially just 2 steps, and the 1 step is repeating step 1 and 2. So pretty simple method, actually, if you look at it like this, right? Yeah, but one of the crucial parts of recursive feature elimination is the elimination of the model coefficients or model weights. So to kind of like illustrate this, I have for reference a linear regression and a logistic regression model here. Linear regression, as you may know, is for modeling continuous targets, whereas logistic regression is a classifier for targets that are discrete or categorical labels, as we know. I don't want to go into too much detail because that's already covered in other lectures, right? So we had, most of you probably know how linear regression works, and we have also discussed logistic regression before. Here I'm just showing you 2 figures I made just for reference to show you how similar both models are. So we would use linear regression if we use recursive feature elimination for regression context, and we would use logistic regression, for example, as a model for recursive feature elimination for a classification problem. Both of them have here the model weights or model parameters, where we usually have the bias unit. In linear regression, that's also usually the intercept term. And the model weights are usually, in regression are the slopes, essentially. So, and these are the ones where we, so how it works is essentially we look at, let me clear the slide here. We look at the magnitudes of these model coefficients, and then we eliminate the smallest one. So for example, if we have 0.1, let's say 0.5 and 1.0 here as the model coefficients, we would eliminate the first one, because it's the smallest one. And if we eliminate this model weight, we also imply that we would not consider the first input feature. So we are essentially getting rid of the first input feature. So instead of, let's say, deleting the first input feature, you can also think about setting this weight to 0, right? So that would have the same effect because we compute a weighted sum here. So if this is maybe not quite clear, I have another slide to walk you through an example of logistic regression, how logistic regression again processes the input. We have discussed this sometime before or a different lecture, so I don't want to go into too much detail, but just because it helps here to understand how we eliminate features, I have an example on the next slide. One moment here, let me go to the next slide. Yes, so here we have an example of logistic regression with 2 concrete inputs, and I wanted to show you how to do the computation in logistic regression so that you get a better feeling for why these model coefficients are actually useful for selecting features. And again, I'm going to skip over most of the details of logistic regression because I don't want to make you feel bored. I have another lecture on logistic regression. And yeah, repeating it all the time would make these videos way too long and probably will also make you feel bored. So just for context, let's consider a simple classification example where we have 2 features, x2 and x1, 2 classes, let's say class 0 and class 1 here. And in this case, it just happens that with a linear classifier, we can classify them perfectly. And we also, let's say, assume we have standardized our features. I mean, normalizing them would also be fine, or just having them on the same scale. We just want to have them on the same scale. But just for simplicity, assume we have standardized them so that the features are centered at, let's say, 0. And let's just say in this plot, we have the range between -1 and 1 here. And considering this particular input for x1, that would be approximately, let's say here, and use a different color, would be here, and -0.4 would be, let's say, somewhere here. So we get this particular input feature, and we want to know whether it belongs to class 1 or class 0. Of course, we don't have, or we don't know the decision boundary in multiple dimensions. I mean, we know it, but we can't see it here. It would be trivial to say, okay, it should be class 0 if the decision boundary is like that. But we are here now doing the computation and see why this is without, let's say, having the visual as an 8 here. So in logistic regression, we compute a weighted sum first. We call that the net input. That is essentially multiplying the feature with the model weight. So here, 0.3 times -0.2. Model weight was learned to be -0.2. So this would be x1 times w1. And then here, that would be x2 w2. And then lastly, we have the bias here. Just for simplicity, I set it to 0. So we have a bias unit of 0. And then we get the weighted sum of -0.82. Then we go, or we have a nonlinear activation function, the logistic sigmoid function here. And this is a function that takes inputs the inputs are between -infinity and infinity, and the output is between 0 and 1. And we can interpret this output here, the output of the logistic sigmoid function, as a class membership probability here. So the probability that a data point belongs to class 1 given its feature observations. So here we now plug in our net input into this logistic sigmoid function. We get a 0.3 as the output. So this is our 0.3, our class membership probability that this data point belongs to class 1. And then we have this threshold function, and by default, the threshold is at 0.5, which is just in the center between 0 and 1. And we say if this value from the logistic sigmoid function is greater than 0.5, we return class label 1, and otherwise we return class label 0. Since we have something like here 0.3 that is smaller than 0.5, what happened here? 3.3 smaller than 0.5. I need more practice with this pen tablet here. But since 0.3 is smaller than 0.5, we have class label 0. And then looking here, that makes also sense if we consider this context of this decision boundary. Okay, so what does it have to do now with feature selection? So the bottom line is that everything here depends kind of like on this weighted sum, right? Because the weighted sum determines the magnitude of the value we get from here. So if we make the weighted sum bigger, this value will become bigger. And if this value becomes bigger, then it is more likely, let's say, to exceed this threshold. So making these weights here bigger will help with exceeding the threshold. Let me clear the screen here so we have more to see. So making these weights bigger makes the net input bigger, makes the output from this sigmoid function bigger, and makes it more likely to exceed this threshold. So to make it more likely that it is class 1. And then in this sense, we can consider the weights as how important each feature is, right? Because it's kind of like quantifying the influence of the input feature in a sense. So we can say a large weight gives this input feature a lot of importance when we compute here the net input. And by the way, I mentioned, okay, it's more likely to exceed the threshold, but also can make it more likely to be below the threshold if this is, for example, a negative value, or this is the negative value. We are here mostly interested in the absolute value because that pushes the boundary or the threshold more to the left or more to the right, or whether we are more to the left or more to the right of the threshold. So what's really important is like this magnitude of the weight here. So this kind of like gives us an importance of how much the input feature plays a role when we compute the net input. And again, this is why we want to standardize or normalize the weights so that the input features are on the same scale, which then also have the proportional weights so that we can interpret the weights better. Yeah, and this is already it, how recursive feature elimination works. So in the remaining slides, I want to show you an example in scikit-learn how we can use recursive feature elimination. So we are using the wine dataset again because it has a lot of features. It's a nice dataset for illustrating feature selection. So we start again with preparing the dataset. So here again is the same code I showed you before in a different video. So I'm not talking about this again because it would be quite boring. But again, also if you want to run the code on your computer, I will share the code notebook under the video in a link, so you can also run this code later. I'm just using slides here because it's easier for the annotation rather than, let's say, running it in a Jupyter notebook. So here is also code that we have seen before. So here I'm just splitting the data set into training and test set. And then I'm using my standard scaler to standardize the data. So I'm standardizing it, and then I will be working with xtrain standardized and xtest standardized. Yeah, and this is the real interesting part where we use recursive feature selection. I should have said actually elimination. Recursive feature elimination, short RFE, in scikit-learn. And we are using it with a logistic regression model here. So how it works is we can instantiate a RFE object from the RFE class, and it gets as input an estimator, for example here our logistic regression, and then we can specify how many features we want to select. In the wine dataset we have originally 13 features and we want to select, let's say, 5. Why 5? I mean, this is just arbitrary here, but I will also show you in a few moments how we can, let's say, use grid search to determine what is a good number for the number of features to select. There's another parameter here, step, and step means how many features do we select at a time, because remember the 3 steps in recursive feature eliminations are: step 1 is fitting the model, and then step 2 is eliminating the feature, let's say with the smallest weight. And we could also, instead of saying the one feature with the smallest weight, we can also say, let's say the two features with the smallest weights, right? We could have more than one feature. And step determines how many features we select at each given time. If we have a number that is greater than 1, this algorithm will run a little bit faster because, let's say, it may select 2 or 3 features to eliminate in each round, so we reach the 5 faster. But typically, if we use linear model like logistic regression here, it's a relatively fast algorithm or relatively fast feature selection algorithm, because linear models are very fast to fit, even if the data set is large. So I would in practice recommend just using step 1 here, because why not? Unless you really experience that the method is very slow, then you can maybe increase that. But other than that, I don't think there's a good reason to choose a number that is larger than 1 here. Okay, so once we have instantiated this RFE object, we can then fit it. It behaves just like a normal scikit-learn estimator. So we can fit it to the standardized data. So what's important here is that the data is standardized. And then we can use here the RFE to perform feature selection by using the transform method. So what will happen is, if we use transform, xTrainSub will be a training subset where we have only 5 features now. So the original feature set, let's say, had 13 features. And now, so this would be xTrain standardized, and then xTrainSub would be a data set that only has 5 feature columns. So this would be xTrainSub, a smaller data set. Should have maybe shown shape here, so you would have seen that. But yeah, I didn't, so you have to trust me here. You can try this out in the notebook that I'm sharing, by the way, if you are curious if that's indeed the case. By the way, if we are curious which 5 features it has selected from the 13, there is an attribute called support underscore, and this gives you the indices, a Boolean mask. A Boolean mask essentially means a mask consisting of true and false values. And if we do that, we can see the following Boolean mask, and it gives us information about which features are selected, true, which features are eliminated, false. So the false features are eliminated and the true ones are selected for feature selection. So if we want to know the names of the features, we have in our data frame, the wine data frame, we have the column names. The first column, by the way, was the class label. So I'm skipping the first class label here. And then if I use the Boolean mask as a selection operator, as a fancy indexing selector, then I can get the names of the features that were selected. And in this case, we have alcohol, flavonoids, color intensity, hue, and proline as the most important features in the wine data sets according to our linear model here. Yeah, last but not least, when it comes here to the code examples in this video, I have an example of using recursive feature elimination as part of a scikit-learn pipeline. So why is that useful? Well, it allows us to use, for example, grid search or randomized search or any other hyperparameter tuning method in, let's say, scikit-learn to select a good number of features for our recursive feature elimination object. So here I'm showing you how that works. First, I'm making a pipeline, a scikit-learn pipeline, for example, consisting of the feature selection here, recursive feature elimination, and a k-nearest neighbor classifier. I can put any classifier here, right? So I don't have to put k and n here. I could, in fact, also use logistic regression here, but I thought it might be quite boring. And also, like we have seen in the previous video, if we want to do feature selection, let's say for logistic regression model, we could also just use the L1 penalty, right? So here we use the recursive feature elimination as a general method for feature selection for any type of model. However, also note that logistic regression has the assumption that, let's say we have a linearly separable data set and the selected features or the eliminated features are specific, let's say, to this logistic regression model. So we assume, for example, certain features are important for logistic regression, but then k-nearest neighbor may consider different features as important. So in that case, it's not optimal. It's more like an approximation that we do here. We use a simple model here for feature selection, and then we use the selected features as input to any, let's say, more complicated model, complicated in terms of a nonlinear decision boundary. Okay, but let's maybe continue with this example before we get too sidetracked with assumptions we make here. So we are tuning two things. So first we are tuning the number of features. So the original data set has 13 features. So we are here selecting between 1 and 12 features. So 13 is the upper bound. So it selects, at least it makes the selection. It's not using the original feature set here. And the number of features is between 1 and 12, including 12. And then we are also tuning the number of neighbors. I'm just setting it to the upper bound of 10, but it was kind of arbitrary here. So you can also choose a larger number, of course. Then we are using our grid search CV object on the pipeline we just created with the parameters we want to tune here. And we use tenfold cross-validation, and we run things in parallel on our computer. So we are fitting then the grid search object on the standardized dataset. By the way, you could also just use the regular dataset and use standard scalar here. It would be even slightly better to use the standard scalar here. I didn't do that, but it's also fine. And then we look at the results here. So the best parameters from hyperparameter tuning are a k-n classifier with 3 neighbors. And the method finds that 5 features is ideal here for recursive feature elimination using logistic regression and tenfold cross-validation. And this results in a tenfold CV accuracy of 99%. Just to take a look at how well this feature subset performs on the test set, we get here actually even 100% performance using this pipeline on the test set, which is actually pretty good. So it's, of course, a small test set because it's a small data set in general, but we can see here it's actually generalizing very well. So there is no overfitting, quite the opposite actually. So the test set performance is even slightly better than the training set performance. So it's actually also not the training set performance, I should say, it's tenfold cross-validation performance. And just for reference, I have the full feature set here. And note that we discussed that before, that k-nearest neighbors is prone to the so-called curse of dimensionality. So having too many features given a fixed size data set can make the performance of k-nearest neighbors worse. And in this case, we can observe that. So if we use the full feature set here and train a KNN model on the full feature set with 3 neighbors, and then look at the test performance, we get only 96% compared to the 100 here. So in that case, feature selection is actually good. Okay, so this was an example of recursive feature elimination in scikit-learn. Actually, I have one last slide on recursive feature elimination with scikit-learn, and I just wanted to show you how we can use it also with other models other than, let's say, logistic regression or linear regression. So here in RFE, we have an estimator that we provided, and in our example, we used logistic regression, but we can use any estimator here. So I have the reference here. We can use any estimator that has a coefficient attribute. For example, The linear SVC, support vector machine classifier in scikit-learn, also has that attribute. But we could also, for example, consider any model that has a feature importances attribute. And in the last video, we learned, for example, the random forest classifier would be a candidate that has this feature importance attribute. So we could technically also use a random forest here for feature selection. So we are not limited to anything that is a generalized linear model. However, it's more, let's say, traditional to use a generalized linear model here. Okay, before we end this video, also one short note about the pros and cons, the advantages and disadvantages of recursive feature elimination. So one advantage is that we can explicitly select the number of features we want to select, right? So remember, before we could set it to 5 if we really care about selecting 5 features. One disadvantage though is that, well, we are guessing here, or let's say we have maybe some prior knowledge, that might be something, but most of the time, yeah, there is no way we know what is a good number of features to select, right? So in this case, we usually also have to consider running a hyperparameter tuning technique to find a good number of features, which is, I would say, a disadvantage. One advantage, though, is if we use a linear model, is that the search, or in general, the feature selection is actually pretty cheap. So it's not a very expensive method. In the upcoming videos, I will show you some more powerful methods for feature selection, but they are also more expensive. Then one advantage is also that we are taking feature interactions into account. So what that means is that we are taking the group of features into account. We look at the features together. So if they have a synergistic effect, that gets also incorporated because, right, the let's say logistic regression model considers the combination of features or inputs compared to, let's say, variance threshold that we discussed before, where the variance threshold really just looks at one feature at a time. So it's not modeling any interactions between features, which can sometimes be not optimal if you require, let's say, a combination of features that is only useful if the features appear together. Then one disadvantage is that it has certain assumptions. For example, that the dataset is linearly separable if we consider a linear model. So the linear model has certain assumptions, and we really make these assumptions for feature selection to decide which features are important, but these assumptions may not be necessary if we just consider the final classifier. So basically, I'm trying to say here that we are using a model to approximate what features are important, although this is not our final classifier. And then one disadvantage is also that we are not optimizing the performance metric directly. So we are optimizing essentially what feature is, let's say, important or mostly used, but it doesn't maybe perfectly correlate with the performance of the model that we care about, right? So in that case, it's also not ideal. And in the upcoming videos, I will show you a method that looks directly at the model performance, the predictive performance of the model that we care about to do the feature selection. So in the upcoming videos, we will then talk about permutation importance and sequential feature selection. So see you next time.